Hey everyone, Alex here. On the 21st of March, inside the cavernous, echoing shell of an abandoned power plant right in the heart of downtown Austin, Texas, a coalition representing Tesla, SpaceX, and AI stood up and officially. It is a name that is as audacious as it is politically charged. They outlined a blueprint for a fully integrated, vertically stacked super semiconductor factory. We are not just talking about some minor assembly plant here. We are talking about a facility designed to handle everything from initial silicon architecture and logic synthesis to the most advanced extreme ultraviolet lithography, all the way down to the final packaging and testing. The stated goal is a 2-nanometer manufacturing process node. The initial production target is set at 100,000 wafers per month. The ultimate end-state vision is to churn out 100 billion to 200 billion artificial intelligence chips every single year, pushing their total aggregate compute power into the exaflop and zettaflop ranges, effectively trying to build an infrastructure capable of handling exawatts of power. When this news dropped, the market immediately reacted. Some tech blogs called it a masterstroke. Retail investors started cheering, assuming that if anyone can single-handedly replace the entire semiconductor supply chain of the island of Taiwan, it is the guy who figured out how to land orbital rocket boosters. But before we start applauding and pricing in a total monopoly on global compute, we need to take a massive, sobering step back. The laws of physics do not care about your valuation, and they certainly do not care about your media narratives. As an engineer, when I look at the physical realities of what they are proposing, I see a project that is colliding headfirst with the fundamental limits of thermodynamics, quantum mechanics, and material science. We have to dissect whether this is a genuine technological revolution or a $20 billion delusion. Why is Elon Musk trying to do this? To understand the motivation, we have to look at the sheer terrifying scale of his compute requirements. He is not doing this out of pure ego. He is doing it out of a deep existential fear. He is terrified that Taiwan semiconductor manufacturing company Samsung and Micron will simply not be able to build fabrication plants fast enough to supply his companies with the silicon they need to survive the next decade. There are 4 massive simultaneous cash-burning engines currently driving this desperation. The first engine is the continuous iteration of Tesla's full self-driving software and the impending mass production of the Cybercab. To process the millions of gigabytes of video data pouring in from the global fleet, they need the next generation of AI inference chips, internally dubbed AI Lu. The volume of these chips required is staggering. Every single vehicle rolling off the line needs serious onboard compute. The second engine is the Optimus humanoid robot program. They are projecting millions of these units operating in the real world. You cannot run a bipedal robot that has to dynamically balance and interact with unpredictable human environments by relying on a cloud server connection. The latency will kill the functionality. The robot will fall over before the server tells it to adjust its ankle actuator. Every single Optimus needs a highly capable, highly efficient edge computing chip physically located inside its chassis. The third engine is Zat-I. Training massive large language models like Grok requires monstrous supercomputers. We are talking about clusters of tens of thousands of processors. This requires bleeding-edge logic accelerators and highly complex high-bandwidth memory architectures, all operating in perfect synchronization. The fourth engine, and perhaps the most scientifically insane, is the Space Compute Initiative. SpaceX wants to put data centers in low Earth orbit, integrating AI chips directly into the Starlink satellite constellations. When you add all 4 of these massive demand curves together, the internal projections at Musk's headquarters indicate that within 3 to 4 years, they are going to hit a brick wall. The global foundry capacity will simply be exhausted. They will be stuck in a queue waiting for chips while their competitors catch up. So the logic dictates that instead of being at the mercy of external suppliers, they should just build the factory themselves. It is the ultimate expression of first principles thinking. Speaking as a serial founder, I understand this impulse completely. When I see a critical bottleneck in my supply chain that I cannot control, my immediate instinct is to bring it in-house. You want to own the machine that builds the machine. It makes perfect sense on a spreadsheet. But here is the massive cognitive trap they are walking into. The logic is sound, but the engineering execution requires crossing an ocean of complexity that money simply cannot buy. Musk's teams are undeniably brilliant at designing chips. They poached legendary chip architects from the industry. They brought in Jim Keller's disciples. They recruited Peter Bannon from Apple, a guy who helped design the foundational silicon that powered the iPhone revolution. The inference chips that Tesla currently uses inside their cars are custom designed in-house, and their performance per watt is objectively fantastic. But there is a monumental, catastrophic difference between designing a chip and actually manufacturing a chip. Designing a chip is a software exercise. It involves logic synthesis, architecture layout, optimizing instruction sets, and compiling code. To put it bluntly, you are sitting at a computer workstation drawing incredibly complex, multi-layered city maps. Manufacturing a chip, however, is a completely different universe. You are no longer drawing a map. You are building that city at the atomic scale. You are manipulating matter using advanced chemistry, plasma physics, and metallurgy. Every single step out of the thousands of steps required must be executed with zero margin for error. Jensen Huang, the CEO of NVIDIA, spoke about this exact issue during a public event in Taiwan. He explicitly stated that trying to replicate the manufacturing capabilities of TSMC from scratch is practically impossible. He pointed out that building a fabrication plant is not just about pouring concrete and buying expensive tools. It is about mastering a symphony of science, process engineering, and the unspoken, undocumented intuition that thousands of technicians have built up over decades of trial and error. Jensen Huang is not just being polite to his suppliers. He runs the most valuable fables semiconductor company on the planet. He understands the chasm between a digital schematic and a physical silicon wafer better than anyone. And yet, Project Taiwan B is aiming straight for the absolute hardest target on the board, which is the 2nm process node. Let us break down exactly what 2nm means, because this is where the system collapse begins. Moving to 2nm is not just a standard upgrade. It is not like moving from an iPhone 14 to an iPhone 15. The entire semiconductor industry is being forced to abandon the FinFET transistor architecture that has served us well for a decade. To get down to 2nm, you have to transition to an entirely new paradigm called gate-all-around, or GACIA, where the electrical channel is completely surrounded by the gate material using stacked nanosheets. This is not an upgrade. This is ripping out the engine of a commercial jet while it is flying at 30,000 feet and trying to replace it with a scramjet. Material science has to be completely reinvented. The precision of the deposition equipment has to double. Defect management protocols have to be torn down and rebuilt from scratch. If your chemical-mechanical polishing step is off by a fraction of a nanometer, if the dose of extreme ultraviolet photons is slightly too high, if your plasma etching time is off by 1 single millisecond, and remember, we are not talking about breaking one single chip. We are talking about destroying an entire 12-inch disk of silicon containing hundreds of potential processors. In the world of semiconductor economics, there is a ruthless, unforgiving dictator known as the yield rate. The yield rate is the percentage of working chips you get from a single wafer. It does not care about your business plan. It does not care about your press releases. It will destroy your profit margins without a second thought. Yield is inversely proportional to defect density. Let us look at Intel. Intel is one of the oldest, most experienced, most heavily funded semiconductor manufacturers in the history of human civilization. They have been doing this for 60 years. Yet on their advanced nodes, yield issues have tortured them for years. Leaked reports regarding their upcoming 18A node, which is their equivalent to 2nm, suggested an initial defect density of 0.4 defects per square centimeter. Let us run the math on that. In engineering terms, this is a classic single point of failure that cascades through the entire financial model. An NVIDIA H100 GPU has a die size of 814 square millimeters. If you apply a defect density of 0.4 to a chip that massive, your yield drops so low that the project completely loses its commercial viability. It would cost you more to manufacture a single working chip than you could possibly sell it for in the open market. Intel, with its 60 years of institutional knowledge, struggles with yield. Project Taiwan B is starting from zero. They have no historical defect databases to train their machine learning models on. They have no institutional memory of process integration. They do not have the thousands of veteran engineers who can look at a scanning electron microscope image and intuitively know which gas flow rate needs to be tweaked. You cannot buy that experience. You can only earn it by throwing billions of dollars of ruined wafers into the garbage over a period of many years. But the lack of experience is only the first nightmare. The equipment supply chain is an even more impenetrable wall. To build a 2nm chip, you absolutely must use extreme ultraviolet lithography, or EUV. There is exactly one company on the planet capable of building an EUV machine. That company is ASML, located in the Netherlands. They hold an absolute unbreakable monopoly. The entire modern world runs through their order books. TSMC begs them for production slots. Intel begs them for priority shipping. Samsung waits in line, just like everyone else. A standard ASML EUV machine costs around $200 million. The next generation high-NA EUV machines, which push the resolution limits down to 8 nanometers, cost significantly more. But the real problem is not the price tag. The problem is that you cannot buy them even if you have the cash sitting in a bank account. By the end of 2025, ASML's backlog of orders was sitting at nearly 39 billion euros. That backlog is larger than their entire projected revenue for the following year. 65% of that backlog is purely for EUV equipment. The entire world is clamoring for these machines. ASML does not need a new customer. If everything goes perfectly, the lead time to get one of these machines delivered is 12 to 18 months. TSMC has already locked up a massive chunk of the future inventory. Intel has locked up theirs. Samsung is aggressively waiting for theirs. For Project Taiwan B to hit its initial target of 100,000 wafers a month, they would need dozens of these EUV machines, representing billions of dollars in capital expenditure just for the lithography bays. To hit their ultimate goal of 1 million wafers a month, they would need hundreds of machines. They would essentially need to commandeer ASML's entire global output for several years. Do you honestly believe that ASML is going to tell their most reliable, multi-decade partners like TSMC and Intel to wait, just so they can ship their most critical hardware to a brand new, unproven? It is a logistical impossibility. Look at what happened to Samsung. Samsung is the second largest semiconductor manufacturer in the world. They committed $17 billion to build a new fabrication plant in Taylor, Texas. They have decades of foundry experience, yet their project turned into a disaster. The EUV equipment was delayed. The production start date was pushed back repeatedly, slipping well into 2026. The main reason was that they could not secure enough guaranteed customer orders to justify spinning up the massive capacity, and they struggled with the local supply chain integration. If Samsung, a titan of the industry, suffers massive delays and cost overruns just a few miles down the road in Texas, what makes anyone think a completely inexperienced team is going to execute perfectly? But let us suspend disbelief for a moment. Let us pretend Musk somehow gets the machines. There is a physical dead end built into the very location they chose. Project Taiwan B is located right next to Giga Texas, the massive automobile manufacturing plant. They are starting with 2 million square feet and talking about expanding to 10 million square feet. Do you understand how sensitive 2 nanometer lithography is? We are talking about ISO Class 1 cleanrooms. The air inside these rooms is thousands of times cleaner than a sterile hospital operating theatre. The optical systems inside the lithography machines have to align themselves with sub-nanometer precision. A minor seismic event halfway across the state can ruin a batch. The vibration from a heavy truck driving on a nearby highway can cause the silicon wafer to blur under the laser. Even the internal mechanical resonance of the building's own HVAC system has to be perfectly damped. And where did they decide to build this hypersensitive laboratory? Right next to a car factory. A factory that uses massive, multi-story tall gigapresses. These are machines weighing thousands of tons that literally slam dies together under immense hydraulic pressure to stamp out metal car chassis. They are pounding the earth over and over again, creating massive, low-frequency seismic shockwaves that travel directly through the bedrock. You cannot put a 13.5 nanometer wavelength extreme ultraviolet laser next to an industrial stamping press. From a systems architecture perspective, placing these two operations adjacent to one another is a fundamental violation of physical isolation principles. They are physically incompatible. Musk's team has proposed a highly experimental workaround. They want to ditch the traditional massive cleanroom architecture. Instead, they plan to use localized sealed microenvironments. The wafers would travel entirely inside ultra-clean pods, moving from tool to tool. Now, using sealed front opening unified pods is already an industry standard for transport, but totally eliminating the surrounding cleanroom environment for the actual tool loading interfaces is incredibly risky. How do you prevent microscopic particulate contamination during the exact moment the pod opens to transfer the wafer into the vacuum chamber of the lithography tool? They are gambling tens of billions of dollars on an unproven experimental facility design because they boxed themselves into a bad geographic location. And then we have to talk about the space computing aspect, which is perhaps the most heavily promoted and least understood part of this entire narrative. Musk argues that the terrestrial power grid is simply too slow to expand. He claims that 80% of future AI compute will be deployed in orbital data centers. He points out that solar panel efficiency in space is 5 times higher than on the ground, because there is no atmospheric scattering, no weather systems to block the sun, and no day and night cycle if you position them correctly. The plan is to use the terabit optical laser links from the Starlink version 3 satellites to network all these orbital processors into one giant distributed supercomputer. The energy generation logic is actually quite sound. The fatal flaw is thermal dynamics. Down here on Earth, when you run an AI server rack, it generates a massive amount of heat. We manage that heat using high-velocity forced air or complex liquid cooling loops, and ultimately, we dump that thermal energy into the Earth's atmosphere. The atmosphere acts as an infinite heat sink. In the vacuum of space, there is no air. You cannot use convective cooling. The only way to remove heat from a satellite is through thermal radiation. You have to radiate the infrared energy out into the blackness of space. Radiating heat is incredibly inefficient compared to convection. It requires massive, heavy, deployable radiator panels. Modern AI accelerators easily pull 700 to 1000 watts of continuous power per chip. To cool thousands of those chips in a vacuum, your satellite would need radiator wings the size of football fields. And if you fail to cool them, disaster strikes instantly. If a semiconductor runs too hot, you experience severe subthreshold leakage. The transistors physically cannot turn off. Current continues to bleed through the gates, which generates even more heat, driving the temperature higher, causing more leakage, resulting in a rapid thermal runaway event that melts the silicon. Furthermore, elevated temperatures increase the electrical resistance of the interconnects, which raises the RC time constant, forcing you to drastically lower the clock speed of the processor just to maintain stability. Your exaflop orbital computer suddenly throttles down to the speed of a smartphone, and that does not even factor in the radiation environment. Low Earth orbit is bombarded by cosmic rays and high-energy solar protons. When a high-energy particle strikes a silicon die, it can cause a single event upset, literally flipping a digital 0 to a 1, corrupting the AI calculation. To make a chip radiation hard, you have to design redundant logic circuits. You have to add thick oxide layers. You have to use specialized silicon on insulator manufacturing techniques. Every single of these radiation hardening methods drastically reduces the performance and increases the physical size of the chip. A space-rated AI processor will always be significantly slower, larger, and vastly more power-hungry than its terrestrial equivalent. All the free solar energy you captured in orbit is immediately consumed by the massive overhead required to cool the chips and protect them from radiation. You are literally paying a massive tax to the laws of physics. Some defenders of the project will say, look at SpaceX. Everyone said landing rockets was impossible, but he did it. Therefore, he can figure out chip manufacturing. As someone who has scaled hardware lines, I can tell you right now that this analogy is fundamentally broken. A rocket engine is a macro engineering problem. It involves fluid dynamics, metallurgy, thermodynamics, and pressure vessels. You can look at a rocket valve with your eyes. You can measure it with calipers. You can attach thousands of physical sensors to it. If it fails, you analyze the telemetry, you machine a slightly thicker valve, you bolt it on, and you launch again. You can iterate through rapid, explosive prototyping. Chip manufacturing is nano-engineering. It is governed by the probabilistic rules of quantum mechanics. At the 2 nanometer scale, electrons do not behave like particles. They behave like waves. They can literally teleport through the insulating barriers via quantum tunneling. You cannot visually inspect a quantum defect. You cannot rapidly iterate a chemical vapor deposition recipe because it takes 3 months just to run one batch of wafers through the fabrication line to see if your tweak actually worked. The learning cycles operate on entirely different timescales. You can overcome macro engineering challenges with brute force, capital, and relentless iteration. You cannot brute force an atomic lattice. So, does this mean Project Taiwan B is completely doomed and destined to be a total write-off? Not exactly. If you look closely at the supply chain movements, a very different, much more pragmatic strategy emerges. The real breakthrough they are aiming for is not actually in the front-end extreme ultraviolet lithography. The real play is in the back-end advanced packaging. For the last 3 years, the entire global AI hardware industry has been severely bottlenecked. The constraint has not been manufacturing the raw logic dies. The true choke point has been the advanced packaging process, specifically the complex techniques required to integrate the logic chips alongside high-bandwidth memory modules onto a single interposer. TSMC's proprietary CoWoS packaging capacity has been critically overwhelmed. NVIDIA essentially bought up the entire allocation, leaving every other company scrambling for scraps. Musk's underlying strategy here is actually quite brilliant. He can continue to purchase the raw silicon wafers from TSMC or Samsung, effectively letting them deal with the 2 nanometer yield nightmares. But by bringing the final advanced packaging process in-house, he bypasses the TSMC packaging bottleneck entirely and regains total control over his final product assembly. There is hard physical evidence supporting this theory. SpaceX has been quietly building a state-of-the-art advanced packaging facility in Bastrop, Texas. They are utilizing a technology called fan-out panel-level packaging. Instead of packaging chips on standard circular wafers, they are placing them on massive rectangular organic substrates measuring 700 by 700 millimeters. To give you some context, the standard industry panel size is usually limited to 600 millimeters. By moving to a larger rectangular format, the geometric efficiency skyrockets. You waste far less space near the edges compared to a circle, allowing you to package up to 2.5 times more chips per run. Furthermore, they are using organic materials and semi-additive manufacturing processes. They are utilizing copper electroplating combined with precision laser drilling to create the microscopic vias. They are completely avoiding the massively complex and fragile glass substrates or silicon interposers that traditional packaging requires. The technical barriers to entry for this type of organic panel-level packaging are significantly lower than front-end lithography, and the path to high-volume mass production is much faster. Looking at their business model canvas, they were missing the most critical component for autonomy, which was supply chain control. This packaging facility solves that problem. This is a realistic, achievable engineering objective. The grand vision of a fully integrated 2 nanometer megafab is highly likely just a smokescreen. The actual executable business plan is to rapidly scale up these panel-level packaging lines to ensure his companies are never starved for finished compute hardware. We have seen this exact playbook from Musk before. Remember the massive Battery Day presentation in 2020? He unveiled the revolutionary 4680 battery cell format. He stood on stage and promised the world that by 2022, they would achieve 100 gigawatt hours of internal production capacity, slashing battery costs by over 50%. What actually happened? By early 2025, their real-world production run rate was barely hovering around 20 gigawatt-hours. The dry battery electrode manufacturing process, which was the core innovation supposed to save all that money, proved incredibly difficult to scale. They were forced to continue relying on traditional wet slurry processes from external chemical suppliers. It took them 5 years just to reach 1/5 of their initial stated goal. Battery chemistry operates at the macro and micro scale. The tolerances are measured in millimeters and micrometers. Semiconductor manufacturing requires tolerances measured in angstroms, which is literally the width of individual atoms. The precision requirements are 6 orders of magnitude higher. If the battery project was delayed by 5 years, a from-scratch advanced semiconductor fabrication plant will face delays that could span decades. And then there is the brutal reality of corporate finance. When I look at this cap table, the numbers are terrifying. Let us run the actual math on this endeavor. The projected capital expenditure for 2026 alone is anticipated to exceed $20 billion. When you stack the enormous capital drain of Project Taiwan B on top of the existing automotive and robotics research and development budgets, their free cash flow is projected to plunge into negative territory. What does that actually mean for the company? Tesla's total cash reserves are currently sitting around $44 billion. This single semiconductor project threatens to incinerate over 11% of their entire cash stockpile in a single 12-month period. This is a staggering burn rate. If the project faces the inevitable engineering delays we just discussed, that burn rate will accelerate. They will absolutely have to return to the capital markets to raise more money. They will have to issue new shares or take on massive debt, which will heavily dilute the value for existing shareholders. Major institutional banks like Morgan Stanley and Deutsche Bank are still issuing buy ratings with massive price targets ranging from $400 to $500 per share. But you have to understand what those analysts are actually modeling. They are completely ignoring the core automotive business, which is currently showing severe signs of demand softening, with late 2025 delivery projections being revised downward across the board. The banks are valuing the company entirely as an artificial intelligence pure play. They are pricing in the immediate, flawless execution of the Optimus humanoid robot, replacing global manual labor, and the Cybercab fleet monopolizing the global ride-sharing market. But if that AI narrative stumbles, if the actual deployment of these technologies is delayed by regulatory hurdles or software limitations, or if Project Taiwan B suffers the exact same multi-year timeline slippages as the cash flow destruction will be violently exposed. The premium valuation multiple will collapse, and the stock price will crater as the market realizes they are funding a multi-billion-dollar science experiment with no near-term return on investment. Let us zoom out and look at the macro picture. What Project Taiwan B is attempting to do is something that the entire global tech industry has recognized as impossible for the last 60 years. They are trying to vertically integrate chip design, front-end atomic manufacturing, and back-end packaging all under one single corporate roof. TSMC spent 30 grueling years backed by the entire industrial policy, educational system, and subsidized infrastructure of the government of Taiwan just to master the manufacturing slice of that. Intel, a company with practically unlimited financial resources and a deep, multi-generational engineering culture, tried to pivot back to a foundry model and is currently fighting for its life, discovering that Elon Musk wants to start from a patch of dirt in Texas and achieve all of this simultaneously in just a few short years. The probability of achieving full stack, 2-nanometer high-volume commercial production within this decade is, statistically speaking, 0. However, if we view Project Taiwan B not as an immediate product launch, but as a long-term, multi-phase geopolitical strategy, it starts to make a terrifying kind of sense. Phase 1 is the advanced packaging, securing the assembly bottleneck. Phase 2 is slowly, painfully learning the front-end process over the next 10 to 20 years. Semiconductor manufacturing is a brutal, unforgiving discipline. It does not reward visionary PowerPoint presentations. It does not care about your social media reach. It only respects the cold, hard mathematics of the yield curve. There are no shortcuts at the atomic level. You cannot hack the system. You just have to grind through millions of ruined silicon wafers, until you finally get it right. But this entire saga exposes a fundamental truth about the 21st century. The entity that controls the manufacturing of advanced silicon controls the future of artificial intelligence, and by extension, controls the strategic supremacy of the next 100 years. Right now, TSMC's production schedule dictates the economic and military capabilities of entire superpowers. This is no longer just a hardware business. This is a matter of national survival. So, Elon Musk is pouring $20 billion into a factory that defies the laws of physics and financial gravity because he realizes that if he does not own the foundational layer of compute, his entire empire he might fail spectacularly. He might burn billions of dollars and end up with nothing but an empty concrete shell in Austin. But from his perspective, the existential cost of not trying is infinitely higher than the financial cost of failing. The atoms do not care about his vision, but he is going to spend $20 billion trying to force them to bend to his will anyway.